All right, back from break. So we had been taking a look at chapter 11, working on chapter 11 here, and what we found is that there's this vector operation called a cross product, where we can combine different components of two different vectors to get a different vector. So we combine two vectors together and we get a different vector. That cross product of the two vectors is perpendicular to the original two vectors that we were working in terms of. It's perpendicular to each one of those. And then we said that in general, we can generalize this cross product in terms of a torque, so that the torque is measured relative to a point rather than to an axis. So this becomes a more general way of thinking about these torques and about angular momentum. So here's a torque vector. Let's see if we can use this cross product that we've introduced. Suppose that we have a lever vector. It's in the xz plane, and it's given by 1.2 meters in the x and 1.2 meters in the z directions. Okay, so you can try drawing these, and I think it's a good idea to try drawing them. Sometimes it gets hard to visualize what's going on, but we'll do our best here. And then it says we have a force. The force is exclusively in the x direction. And so calculate the torque for this setup. So we've got a, so here we go. So what I did was I drew an xz coordinate system. So I put x here, I drew z here. Now that means that y is into the board. The way our coordinate systems are set up, we use what are called right-handed coordinate systems. That says that x cross y is z. So if I had y coming out of the board, that would be what's called a left-handed coordinate system. Go back to your math books and see, whenever they show a three-dimensional coordinate system, it's always set up so that if x is my thumb and y is the direction of my finger, on my right hand, y is the direction of my fingers, then z is in the direction my palm is facing. So you've been working with right-handed coordinate systems whenever you do 3D in pretty much all the math applications. That's a convention that we work from. So what we're doing then is we're saying, here is the point around which we want to measure torque. So there's going to be some amount of torque around that point. Here is the lever distance. Now the lever distance had components x and z, but there was a zero here. And whenever there's a zero, when you're doing a cross product, there's, a little cheer goes up. People go, yes, it's zero. That saves me some calculating. So, because here's what the whole formula looks like, right? The whole formula means I got to go in and do 6 multiplications, and then I got to subtract stuff. So sometimes, well, if there's zeros, some of that will be eliminated. So, oh, and here's the stuff I was talking about with the coordinate systems. So if this is the unit vector in the x direction, unit vector y is into the board, unit vector z is here, we need to have ex cross ey is equal to ez. Now the book is using ijk, but it works the same way. I crossed with j equals k. They're all unit vectors. They're all at perpendicular to each other. All right, let's put the numbers in. So 1.2, but this one's 0. That we said was a good thing. And then for the force is entirely in the x direction. So again, I can look at the diagram and see where this torque will end up being. This is 150 newtons, but this is 0, this is 0. So I wrote out the whole set of formulas, and then I started crossing stuff off. Because y is equal to 0, so that goes away, that goes away. Fy is equal to 0, so that goes away. I didn't cross that one out. That one goes away. I didn't get these last two crossed out. That one goes away. And then Fz goes to 0, and that means that one crossed out twice. That was already 0. And this one goes to 0. So the only thing left that is non-zero is that right there. It says the only torque that was non-zero was the one coming from the z component of the lever distance times the force in the x. And I can see that from my diagram. So I can look at my diagram and go, oh yeah, I can see that this part of the lever distance did not give us any torque because it's lined up with the force. It's not perpendicular. This is the component that's giving me torque. So it's specifically this component of lever times this component of force that's giving us the torque. And it worked out to be, uh-oh, did we actually not calculate that number? Oh, we did, good. Okay, so here we are on the next page. And what we ended up with was a torque 0 in the x direction. Let's go back and see. So the only torque we have is in the y direction, and it's positive. Now, if I put my thumb in the direction of the y, it says this torque will create accelerations in this direction. And I go, yeah, that's it. If it's around this point, the torque that we have is going to tend to create rotational accelerations in that direction. All right? So again, it's a systematic way to go in and carry out the calculations. Now, how this gave us 180 newtons times meters. Now, what if we just work from the vector diagram? So the vector diagram for this would look like, here is R, here is F, and there's an angle between them. Now, the right-hand rule tells me that if I put my thumb in the direction of the first vector and my fingers in the direction of the second vector, my palm is facing the direction of the cross product. That would be the torque. Now, we've got the direction figured out. The torque's going to be in the positive y direction. How do we figure out magnitude? Now, we did all the components, but we said the other way to find out what the magnitude would be to take the magnitude of F, the magnitude of R, times the sine of the angle between them. So R would be equal to x squared plus, that should be z squared. So x squared plus z squared to the half is 1.70 meters. And plugging that into here, the force was 150. I'm going to put in the sine of 45 degrees. That's the angle between these two vectors is 45 because the x and the z components match. And so I can use this formula to calculate the very same number. And often that's going to be an easier approach. So it's more common for us to use this formula, let me just say that, compared with using this full set of formulas, but you should be prepared for either one. And you should practice using both approaches. Okay, that's how it works. Now, the angular momentum of a particle, so they've got some kind of an object here and it's got mass. The angular momentum can also be written as a cross product. This can be written as the lever distance cross the linear momentum. We said there's a relationship between linear momentum and angular momentum, and that's it. So I can take the linear momentum, cross it with the lever distance, and that will tell me how much angular momentum we have relative to some point. And so that's kind of interesting too, because you go, well, does an object just have angular momentum, or does it have to be relative to some location? And it has to be relative to some point. So we have to be working within some coordinate system and determining what the angular momentum is being measured relative to. All right, here's a bunch of derivatives taking of the angular momentum, and what they're showing is this. They're showing that if angular momentum is lever distance cross linear momentum, we could take time derivatives of both sides. And what we'll be able to show from that is that the torque determines the rate at which angular momentum is changing for an object. So the torque transfers in angular momentum. That's what that math is telling us. Let's see how that actually applies in an example. And so here we go. This is one that we've seen examples like this before. Here is an origin. Here is some point around which we are going to do some measurements. What is the angular momentum of an object with mass m moving with speed v in a circle of radius r in a counterclockwise direction? And so we've seen this. Now, the way this is set up is that this object has linear momentum that's given by m times the velocity vector. So when I calculate the angular momentum, that will be r vector cross momentum, linear momentum vector. And that can be written as m r cross v. Now the angular momentum then, also the magnitude would be the magnitude of r times the magnitude of p times the sine of the angle between them. If that's in circular motion, if that particle, if that mass is in circular motion, then the lever vector will be perpendicular to the momentum and perpendicular to velocity. So this is going to become rp times the sine of 90 degrees. And the sine of 90 degrees is 1. And that's how you get the largest cross products, is by having your two vectors perpendicular to each other. Now, that could be written as r times momentum, or it could be written as r times m times v, which was one of the formulas we started the chapter out with. Okay, so we're back to r times m times v. Now, again, I want to go back and kind of emphasize this vector diagram. We've done these from time to time. These have come up. Here's a diagram showing where objects are located, and then we've placed vectors to represent different physical quantities. But when we do a vector diagram, what we do is we lift up these vectors and move them onto a different coordinate system where every vector is placed in relationship to the origin. So here, I've got these two vectors, and if you ask, what's the angle between these two vectors? It's easy to get confused. And so what you can do is you can rewrite the two vectors in that fashion. So if I write the two vectors in that fashion, then it becomes pretty clear the angle between them is 90 degrees. Okay. And with 90 degrees, this is not as crucial, but this is a good general way to analyze what's going on in terms of vector orientation and what's the angle I have between the two vectors that I'm looking at. Also, in terms of direction here, once I've got, how do I do a right-hand rule here? And that's a little complicated, or it might be. This makes it a bit easier. Here I can put my right hand right up to those two vectors. My thumb is in the direction of r, my fingers are in the direction of p, and r cross p gives me a palm direction coming out of the page. So my palm is facing out of the page. That would be the direction of the angular momentum vector. Okay, now there's some stuff here that we're not, we want to go through some of these ideas conceptually and understand what's going on. The math itself we're not necessarily going to be using here, but it says that the angular momentum of a system of objects can only change if there's an external torque. So a good example of this would be like a planetary system, something like the solar system. We've got the sun, we've got all the planets, and as the planets are orbiting the sun, the planets exert forces on each other. Now, the solar system, we could treat it as if it's isolated from other star systems. So we could take individual star systems and say that all of the planets are exerting torques on each other. Like there's the Earth and the Moon exert torques on each other, and that has resulted in slowing down the rotational rate of the Earth and the Moon. The Earth is not rotating as fast as it was, hundreds of millions of years ago, and the Moon is just flat out, in some sense, stopped rotating, right? The same side of the Moon always faces the Earth. Now, what happened to that angular momentum? We expected in the early solar system, the Moon was rotating at a higher rate. The Earth was rotating at a higher rate. That's gone into orbital angular momentum. So you may be aware that the Moon and the Earth are moving farther away from each other very slowly, and that additional angular momentum is coming from the slowdown of the Earth and the Moon. So angular momentum can transfer back and forth between different planets or different moons within the solar system. So what this is saying is, if we are able to isolate a bunch of objects, then we can show that any changes in the angular momentum within the system would have to come from outside sources. Otherwise, all of the changes in angular momentum are happening within the system between different objects. Okay, so again, if we assume that the solar system is isolated and that there's no external torques, then the total angular momentum of the planets and the Moon and the Sun and everybody remains a constant, even though that angular momentum can be transferring back and forth between different objects within the solar system. Okay. All right. Let's take a look and see do some angular momentum calculations for objects. For a rigid object, we can show that angular momentum around a particular axis is given by angular momentum is I omega. Now, that really only works if we're calculating this around an axis of symmetry through the center of mass. So let's say that we have a cylinder here, and what we can do is we can look at individual parts of the cylinder and ask how much angular momentum each individual portion of the cylinder has. When we do that, we find that the angular momentum for, say, a point right there, that angular momentum does not line up with the axis of rotation. So that point, if all we had was this one object around this as the point of rotations, the angular momentum would not be fixed. It would not be a balanced system. So in order to get all of the angular momentum to line up with the axis of rotation, we need to have a balanced object. And this cylinder is balanced. And it's balanced because if I look at this point here, and then if I look at a point directly over here, and then corresponding symmetry points along the bottom, all of the lateral components of the angular momentum cancel out. And so it's only in the case where we have a symmetric distribution where the angular momentum, combined angular momentum, lines up with the rotation of the object. Okay, so something to be aware of. This shows up in things like balancing car tires, right? They can go in and spin your tires, and if the wheels and the tires aren't symmetrically placed, then you're constantly wearing on the bearings inside the wheel. And so if you take your car in to have the wheels balanced, they'll spin those and they'll adjust. They'll place different masses onto that so that all of the angular momentum combined lines right up with the rotational axis of the wheel. All right, let's look at a couple of other examples here. These are going to look, I think, more familiar in the homework, for example. So let's say this. Let's say that we've got a cylindrical, it looks cylindrical, we'll see if it is, disk or pulley system. And then what we've got is a couple of objects, MA or M1, MB or maybe M2. And what we're saying is that MB has the larger mass, and so this system is going to accelerate like this. So I'm going to have this side accelerating downward. This one is accelerating upwards, and then the pulley then would be accelerating like that, picking up speed. So it says find the acceleration for this system. How do we do it? So I feel like we could do this back in chapter 10, maybe. Let's see. What I've got is I've got this pulley. It's got a certain mass. I've got object 1 and object 2. They have masses M1 and M2. There's a gravitational force pulling down on each side, and then there's a tension. Now, the key feature here is that's different from back when we did similar problems in chapter 4, is that the tensions on the two sides don't match. Now, why is it that I actually need more tension on this side than on this side? And that's because the pulley now has mass, and in order to get the pulley to accelerate, I need torque. And so T2 is going to need to be bigger than T1. I'm going to have two different tensions set up on the two different sides. That's what's going to happen in this case. So let's take a look at some linear formulas. If I look at the acceleration of object 1 and the acceleration of object 2, I can write the acceleration of 1 as, oh, that's the other way. This is going to be T1 minus M1g divided by M1. And then I can write down the tension, 1, in terms of the M's and the A's. For the second formula, or for the second object, I've got an acceleration downwards. And that means that M2g minus T2, that's the net force. Divide that through by M2, and that will be determining what the acceleration will be. Now, T2 then is equal to M2g minus M2a. Now, what I've got right now is I've got a formula for T1, and I got a formula for T2. How do I put those together? They're not the same tension anymore. So I'm going to have to take a look at rotations. So the rotational formula says that the rotation of the pulley, this is just the pulley, depends on torque 2 minus torque 1 over the rotational inertia, where torque 2, this is tension 2, torque 2 is going to be equal to tension 2 times lever distance r. And that's tended to create a positive torque minus torque 1, which is T1 times lever distance r. So I've got two different tensions creating two different torques. And so the net torque is going to be T2 minus T1 times r. Now, I rewrote the rotational inertia as shape factor m r squared, and then I'm going to take the rotational acceleration and replace that with a linear acceleration and say this is r times alpha. This is T2 minus T1 r squared over cm r squared. The r squareds drop off. And look, we ended up using rotation. We ended up with a formula that tells us how the acceleration will be related to T2 and T1. So now I've got three objects, three equations, and I'm going to piece them all together. I'm going to take this formula for T2, substitute that in. I'm going to take this formula for T1 and substitute that in. I'm going to eliminate the T1s and the T2s. And here's what it looked like. So I've duplicated that. This is where we ended on the previous page. I'm substituting in for T2 here, and then I'm substituting in for T1 here. And then I'm bringing all the terms that have an acceleration to the left side. And then I'm taking everything else over to the right side. When I solve for the acceleration, what I'm getting is m2g minus m1g divided by m1 plus m2 plus shape factor times m. Now this is similar to some examples we looked at in chapter 10, but this is the first time we've actually looked at two different tensions and bringing together three objects, and this is it. So if I look at the system, it's being driven gravitationally. What's happening is I've got the gravity pulling down on M2 being opposed by the gravity pulling down on M1. Now M2 is bigger, so M2 wins out. And the acceleration is in the direction of M2 dropping and M1 rising. This becomes the net external force driving the system, and then the denominator must be the net inertia. So the net inertia then would be M1 plus M2 plus shape factor times m. So that would give us a formula telling us what the acceleration would be. Now, up until now, back before chapter 10, we used to say that the mass of the pulley was so small it could be ignored. If that's the case, then we go back to the formula we had in chapter 4. So you can see, now that we understand how rotations work, we can see how to bring in the effect of the pulley, and it's showing up as a additional inertia. All right, let's look a little bit at riding a bicycle. Now this talks a lot about a spinning bicycle wheel, and I don't know if you guys have ever played around with that, but if you take a bicycle wheel that's spinning and then you try to tip it in some direction, it doesn't go in the direction that you expect it would. It actually redirects in a different direction. So let's see why that is happening. So here's an example you could think about. Let's say here's Earth, here's Moon. Now if the Moon were at rest, it would be pulled towards the Earth and it would crash into the Earth. But because the Moon is already moving, it's got a velocity, it's got a linear momentum to it. When the force acts on the Moon, instead of being traveling in the direction of Earth, it just redirects it. And so what the diagram looks like for that is initially I could do this in terms of velocity or momentum. So let's say the velocity and momentum originally are in this direction, and then at a later time that has been tipped. And so there is this small angular variation that took place. Now the dp, the infinitesimal change in momentum, is actually perpendicular to the momentum. It's sideways, and that is the direction of the force. So what happens is the force redirects the momentum. Now the same thing happens with a bicycle wheel. If you start with a bicycle wheel that is not spinning and you try and tip it in a certain direction, it's easy enough to move in that direction. But when the bicycle is already spinning, what happens is it's got an angular momentum already built up, and so tipping it tends to redirect the angular momentum. And so these two vector diagrams here, they match up. This effect is called precession. And so if we suspend a bicycle tire that's spinning, it'll just rotate. It's kind of like a gyroscope effect that you'll see with bicycle wheels. And this is one of the reasons why learning to ride a bicycle is it's not trivial. You're dealing with all of this angular momentum that's built up in the wheel. Now the angular momentum helps stabilize you on the bike. You know, as you ride a bicycle faster, it's easier to balance. But the angular momentum also, you have to learn how to deal with it. So when you turn the steering one direction, you don't, at least when you're first learning to ride a bicycle, you're getting an unusual response. And so let's take a look at that. So this is riding a bicycle. Here is a top view. We're watching somebody riding a bicycle down the street. Now, the wheels are going around in this direction, and that says that we have an angular velocity, there's a rotational inertia of the bicycle wheels, and from those we can calculate the angular momentum. So when I'm riding along, I've built up a lot of angular momentum in the wheels. Now, if you remember, we had defined directions, vector directions for angular velocity and angular momentum, and it was kind of a coin toss. The way that we had to define the vectors, we either would have to define the vector to be this direction or this direction, and it doesn't look symmetric, right? Because you think, well, if the bicycle wheel is spinning, shouldn't the vector somehow be symmetrically placed? But what we do, and what if you remember, is if the bicycle wheel is spinning one direction, then we put the arrow in one direction. If the bicycle wheel were, if this person were riding backwards, then the angular momentum would be in the other direction. So it took some getting used to thinking about the vectors in that fashion. Now, so when I was in freshman physics and I first learned all this, I couldn't ride my bike for a week, right? I would start riding it, and I would see these vectors would appear in my mind, and I'd crash, right? But I've gotten used to it, and so one way to think about this is these vectors, like angular velocity and angular momentum, they're actually called axial vectors. Vectors that have to do with rotation are referred to as axial vectors, and what they really do is they designate an axis of rotation for the object. So the axis of rotation for that front wheel looks like this, and for me, I have to not think about the direction of the arrow or I crash on my bicycle. So anyway, it's an axial vector, it's along here, and this also is an axial vector and it's here. And yeah, if somebody says, but what direction is the arrow? Then I hurry and draw a little arrow over here, or the other direction. But I focus mostly on the axle, the orientation of the axis as representing that. All right, so let's say that I'm riding my bicycle, and I've got all this angular momentum built up. What happens when I turn? What happens when I rotate the handlebars? Since the angular momentum was here, what rotating the handlebars does is it creates a torque. It creates a torque that redirects the angular momentum. And so when I start to turn this, instead of just the wheel turning, it actually tips me to the left. So it tips the bicycle. Now you can see that as a built-in feature, right? This lower picture shows this. I'm riding along. Here's a balanced rider producing no turning torque. But when the person turns the handlebars, we end up with a torque that tends to rotate the person over to a new direction. And that's what makes riding a bicycle something you have to practice, right? You have to practice and get a feel for what the bicycle response is going to be from the torques that are involved with this. So in this lower picture, what's happening is the bicycle rider is leaning to the left. So if the bicycle rider just leans to the left, then there is a torque that redirects the angular momentum, and the wheel will turn in the direction that you have leaned. So you can see people out riding bicycles without using the handlebars, right? And they do that by leaning left or leaning right a little bit. If I lean left a little bit, that creates a torque because of the offset gravitational force. So here is the normal force, lifting the bike, supporting the bike as it runs along the ground. Here is the gravitational force now. This is going to produce a torque. The tendency would be, if the bicycle wheels weren't already moving, and you were sitting on a bicycle somehow balancing, and you lean to the left, you fall over, right? You would just continue. That torque would tend to rotate you. because the bicycle tires are already rotating, that torque ends up redirecting. The torque here, which is in the backward direction, ends up redirecting the angular momentum so that the wheels automatically turn just from leaning and creating a gravitational torque on the bicycle. Okay. Anyway, I hope that helps. I hope you guys don't crash on your bicycles after going through this and looking at these diagrams. All right, let's see what else we have here in the chapter. The net torque on a system is, if the net torque on a system is, have they got this right? Okay, I think what they want is if the net torque on a system is 0. They're saying if the net torque on a system is 0, constantly 0, then the angular momentum remains a constant value. So maybe I need to get back and see if I can get that edited. The total angular momentum of a system remains constant. Here it's stated down below. If the net external torque is 0. So it's the torque that's 0, then the angular momentum is fixed. Objects continue to rotate in the direction that they are already moving. All right, let's try another one of these kind of homework style examples more. Let's do this. Let's take a projectile. So we got a projectile, it's coming along at a pretty good speed. We have a cylinder that's just sitting there, and the projectile hits the cylinder. What's going to happen to the cylinder if it's on some kind of a rotational axis? And what we would expect is it starts to rotate. You know, this is kind of like an asteroid hitting the Earth, not directly, but kind of glancing along the surface. So again, an object comes in. Here is the center of mass of this system, and the object hits. What's going to happen to the rotation? Now, to keep this simple, what we're going to do is use a fixed axis. Yeah, let's just go ahead and use a fixed axis for this. So we'll say here is a fixed axis right here. We'll have an axis coming out of the page. Here is the object coming in, and it hits, and it puts it into rotation around that axis. Now, this is an inelastic collision, so that says that energy is not going to be conserved. But what still will be conserved is angular momentum. We can actually work in terms of angular momentum. Now, it's pretty clear, once this projectile hits, the object is going to go into rotation, and that rotation represents a certain amount of angular momentum. Where did it come from? Did the projectile coming in have angular momentum? And it must have. Now, this is a little weird, saying that an object that's traveling in a straight line has angular momentum, but it does. And here is why. It has angular momentum relative to that axis. Notice that this object has linear momentum, m times v, and that if it continued to travel, it would miss the axis by a lever distance of r. So we can treat this object as having the projectile coming in relative to this system has an angular momentum, and it has an angular momentum of mv times r. So that's the amount of angular momentum we have to start with. Now, after this collides and sticks to this rotating cylinder, sphere, whatever shape, the angular momentum now is going to be the same, and it can be written as I omega. So I'm going to switch over to the I omega, and let's see. If this is a rotating system here, then what we can say is that the rotational inertia of this object, big M, is some shape factor times m times big R squared. And then what about the rotational inertia of this projectile stuck to the edge of this as it goes around, as it rotates. And that would just be mr squared. So if I have an object with mass m, a distance r from an axis of rotation, that's just going to be an amount of inertia mr squared. Okay, so I can combine the two formulas. What I can do is take mvr, that's how much angular momentum we start with, and set it equal to the angular momentum after the collision has taken place. So that gives us mvr is mr squared plus cmr squared times omega. Solving this for omega says the speed at which this cylinder is going to be, or sphere or whatever, the omega value of that will be given by the speed of the projectile divided by r times the mass of the projectile divided by m plus the shake factor times the mass of the object. Okay, so if we were given numbers for that, we could calculate, and they didn't. So what we're left with is a formula. Now it kind of makes sense. If the projectile is coming in at a higher speed, that's going to make the thing spin faster. If this object has a lot of mass, that's going to reduce the angular momentum, or the angular velocity after the collision takes place. So if big M is really big, that will be slower. If V is really large, that will be higher. Okay, so you can kind of see the effects here by carrying through. And again, what we're working from is angular momentum in a projectile that's just moving in a straight line, and using that to conserve angular momentum and determine the angular velocity. Now, it's an inelastic collision, so I thought it would be useful to go in and ask about the energy also. So the energy, the kinetic energy of the projectile coming in is 1/2 mv squared. The kinetic energy of that rotating system is going to be 1/2 I omega squared, where I is now mr squared plus c bigger mr squared, and the omega that we calculated was given by v over r m over m plus cm squared. So I took the omega that we calculated on the previous page, plugged that in. Okay, everything's there. I just have to be careful and step through the algebra and see what it's telling me. When I cancel out all the things that can cancel out, I am left with the kinetic energy after the collision actually can be written in terms of the kinetic energy before the collision times m over m plus cm. So if I take the kinetic energy after and divide it by the kinetic energy before, it says the fraction of kinetic energy remaining is given by m over m plus cm. Okay, so if the cylinder has essentially really small mass, and the little m is actually bigger, then I'm going to keep almost all the kinetic energy. But if big M is really big, then I could lose most of the kinetic energy in the inelastic collision. Okay, so if these rotational collisions, to try and help think about them, go back to chapter 9 and think of some of the linear collisions, and then kind of work back and forth between the examples. Okay, what happens in terms of rotation? What happens if we're always on what happens if we're on a rotating platform? What will physics look like? And physics is not going to, the formulas that we've developed all throughout the course so far are not going to work the same way if we're on a rotating platform. A rotating platform is not an inertial coordinate system, and there will be artifacts due to the acceleration that's taking place for a rotating system. So for example, if we have a rotating platform and someone on the platform throws a ball, a person standing outside the platform can see that the ball went in a straight line, or in a parabola, it went in projectile motion. But for the person on the platform, because of their acceleration, they don't see the ball traveling in a straight line. okay, or they don't see it following that parabola. They see that it curves to one side. So that's kind of an interesting effect. This effect is sometimes explained in terms of a fictitious force or a pseudo force or a centrifugal force when viewed from within the rotating system. Now, this creates what's called a Coriolis effect. If we have here's a rotating platform. So here we've got a rotating platform, and we can see that if the person throws the ball from point A to point B, that because the person was moving here, the ball is going to get thrown and it's going to travel in this direction. So there's a velocity with which the person throws the ball, but the person themselves is moving. And so from standing outside, we can see that ball is thrown fast. We'll neglect the effects of gravity a bit, and let's just say it goes in a straight line. But the point at B, if there's another person at B, the ball doesn't reach the person at B because they're accelerating. And so they are going faster than the person is at point A, and the ball misses them. So what this gets interpreted as within the platform itself is I threw the ball from point A to point B, but the ball curved. The ball curved away from point B. So this effect is called Coriolis, and what it tells us is this. Now, this is beyond stuff that we would see showing up in the midterm. I don't think there's a Homer problem. There's a problem at the end of the chapter describing kind of this. But let's think about what's happening. For a rotating platform, let's say that on the rotating platform, what we're going to do is we are going to follow an object that steadily makes its way along the platform itself. So this could be somebody standing on the platform and then beginning to walk. There's a line drawn on the platform, and then begin to walk along that straight line on the platform. Now, what happens when we put the platform into motion is that the person's location is given by r equals vt. Now, v we're going to say is a constant. The person's going to walk outwards at a constant speed. But now that the platform is rotating, the angle, the angular location of the person is changing with time. So we'll say that the person's walking with a constant speed v, and that the platform is rotating with a constant angular velocity omega. And what happens as a result is the person is walking in this direction. Let's take some point and analyze this. They're walking in this direction, but there's also a velocity perpendicular. So we'll call that a tangential velocity. Now we know there's a radial acceleration taking place for that point, but there's also going to be a tangential acceleration. And that is happening because instead of staying at one place, the person in this case is moving into regions where the tangential velocity is becoming larger and larger. So as you walk from the inner regions of the platform towards the outer regions, the velocities get larger. And that means in order to keep up, you're going to have a tangential acceleration. So again, if I'm on this platform and it's rotating and I'm trying to walk and balance, I'm going to have to lean a little bit to the direction it's rotating to provide a force for this tangential acceleration. Okay, that's what happens. Now what I've done here, and I don't know if, let's see what the time looks like here. See if we have some time left. We could take a look at this. We've got a few minutes here. So what we could do is we could write down, using polar coordinates, we could say that the person's x and y location, right there, is equal to r cosine theta and r sine theta, where r is equal to vt and theta is equal to omega t. So again, we've got this constant outward radial velocity, and we have this constant rotational velocity taking place. Now, those are the x and y components as a function of time, and the person will end up following a spiral. So as that thing rotates outwards. Now what I did was I just took a bunch of derivatives, and again, this is not required. If you're interested in taking a look at how this works, go ahead and take a look at it or stop by office hours. And so I took a time derivative, dx dt, and then time derivative dy dt to get my velocity components. Now when I did that, I had to use the rules for the product rule for taking derivatives, and it gave me two portions. It gave me a radial velocity, and it gave me a tangential velocity. And then I did another set of time derivatives to get accelerations x and y. And when I did this, I got even a more complicated expression. But what we're able to show is that the tangential acceleration is equal to 2 times omega times v. The radial acceleration also drops out, so the radial acceleration that we've been using now since chapter 5, that shows up as r omega squared. That's the same thing as v squared over r. So again, by taking this rotational motion, converting from r and theta, converting from polar coordinates back into rectangular coordinates, and then taking a couple of time derivatives, gives us kinematic equations for the motion of the object. Once we get to the acceleration components, we can identify the tangential effect, which is referred to as Coriolis, and the radial effect, which we've already derived using a different approach. Now, what does the Coriolis effect lead to? And you guys may have heard, you've probably heard this in your physical science classes, that if you look at the formation of hurricanes and cyclones, in the northern hemisphere and the southern hemisphere, they rotate in opposite directions. And that has to do with the Coriolis effect. What they're showing is if we have a low pressure region, the atmosphere in those areas tend to get pushed into that region. But because of the Coriolis effect, they actually end up following curved paths. The Earth below, it's a rotating platform. And so in terms of the coordinates of the Earth, the coordinates relative to the Earth, there is a curve that occurs, and so you build up angular momentum relative to the Earth itself, and you get the formation of these really powerful storms. Again, the Coriolis acceleration, or the tangential acceleration, is given by 2 omega v. All right, that's a good place to stop with the Coriolis effect. Remember, we're all living on a rotating platform, so these effects do show up from time to time. All right, any questions on this? I know there's some challenging parts in Chapter 11. Take a look at the homework problems, take a look at the examples that we did, the examples in lecture. If you guys have questions on those, stop by office hours.